Okay, so today is our second out of two lectures about this divide and conquer theme. So last time we did selection, linear time selection, and then we did closest pair of points or minimum distance in the Euclidean plane. Both were sort of based on some kind of median style divide and conquer. We'll see different approaches or different ways to divide up the data today. I guess maybe one theme of these problems is that today's problems will be a little more like numerical, I guess, whereas last time was a little more combinatorial. But anyway, hopefully it'll still be as fun as integer multiplication can be. All right. Okay. All right. So certainly you guys know about multiplying integers. So let me set up the problem formally. So you're given two integers as n-bit strings, okay? And the goal is just to compute their product, which is, a 2n-bit long string, okay? Maybe 2n plus 1, I don't know. Okay, and okay, so how do we typically multiply integers? Well, at least the way I was taught in school, I'm going to do base 10 because I'm not a robot. But we 1, 2, 3, 4 times 5, 6, 7, 8, something like this, right? And we would like set up this table, and then we would start being like, okay, that's 32, and I carry the 3s, and I get like 27, I carry the 2, 16, 18, right? And so this came from multiplying 8 times 1,234. Hopefully I did that correctly, right? And then I would move on to 7, right? And I would do 7 times 4, that's 28. We got 21, we carried a 2, so that's 23. 7 times 2 is 14, I'm carrying a 2, I get 16. 7 times 1, carry a 1, and I get like 8, right? And I would do 2 more rows like this, and then I would add everything up at the end, right? And you can do this base 2 as well. In fact, it's easier because you only have to understand what 1 times 1 and 1 times 0 is. You don't have to know the full multiplication table between 1 and 9, 0 and 9, okay? But if you're given n digits, whether it's bits or in decimal, how long would this take if I turn this into an algorithm, if I coded this up? How long does this algorithm take? Oh, O(n) squared, okay? So roughly, this digit, 8, got compared to every digit in the top row, and I went to the next 7 got compared to everyone. So I'm multiplying all pairs of digits with each other. That would also be true if we were doing this in binary. Okay, so the question is, can you do better, right? So of course you might be thinking, who cares? Like, don't CPUs like for fixed width integers have like some special operations? And yeah, that's true. Like 32 bits is going to go really fast on a computer. So this will only possibly be useful if you're multiplying really, really big integers, and maybe you're not. Okay, but there's also some historical significance. I mean, at some level, where's the slide I made? Okay, so at some level, um, multiplying integers, I mean, what could possibly be simpler, right? We've known how to multiply integers for a very, very long time. And sort of in the very early days, this is sort of before, this is still roughly preceding computers to a large extent, and just trying to think about computational complexity abstractly. Okay, so this renowned mathematician, Andrei Kolmogorov, I don't know if you guys are familiar with him, but he's done a lot of stuff, including laying down kind of the foundations of probability theory. So he conjectured that this is the best you can do. The kind of tabular thing that we learned how to do in elementary school is best possible. And he's a bright guy. And he was also using this maybe as a, I mean, just also the thought experiment, because people weren't asking this kind of question very much at the time. People weren't thinking about the computational complexity of anything, really. So this is one of the kind of earlier historical times where we're just even asking, what's the best way to do something mechanically, computationally. Okay. All right. So he went around asking if n squared was best possible. He was running an early seminar in Russia, and then surprisingly, Karatsuba, who was I think a graduate student at the time, he was very young, showed up and surprisingly had a better than n squared algorithm, and that's what we'll discuss today, right? And part of the takeaway is like, oh, geez, we didn't even know the best way to multiply integers, right? Seemingly we knew everything about that. There shouldn't be any mystery in that. And so that suggests, oh, maybe there's a lot of things that we can do better if we sort of took a slightly different perspective. So there's some historical significance to this result. Okay. All right. So much for that. So I thought I'd give you guys a chance to guess, at least those who haven't seen this before. So we're going to try to do divide and conquer algorithm and do better than this kind of natural n squared algorithm. Okay, so your input is, again, 2 bit strings of length n. Any ideas of how to do a divide and conquer? What are some ideas for dividing the input? You have 2 n-bit strings. And by 2 bits. Okay, so that's a great suggestion. So we can try dividing the bits in half. Okay, so on top that's supposed to represent all of x as a bit string, but the first half I'm calling x sub 1, that's an n over 2 bit string. The second half I'm calling x sub 2, that's another n over 2 bits. Okay, same with y. y1 and y2 represents the bigger and the smaller half. So that means x is sort of like x1 bit shifted n over 2 times, which is the same as multiplying by 2 to the n over 2, plus x2. And y would be y1 times 2 to the n over 2 plus y2. Okay, so I just want to get the notation clear. It's a little confusing. So x1 is a n over 2 bit number representing the largest n over 2 bits, but itself can be thought of as a number between 1 and 2 to the n over 2, or 0 and 2 to the n over 2. Okay, so if we did divide and conquer, then I don't know. We can, for example, just kind of write out this kind of thing. So if I just distributed, right? If I multiplied, x1 to the n over 2 plus x2 times y1 to the n over 2 y plus y2 and just distributed, right? A plus b times c plus d is like a times c, and so on. Okay, then we would get, well, 4 multiplications was half the number of bits, right? So x1 times y1, that's multiplication 2 of them, of n over 2 bits. And then I have 2 multiplications in the middle. Those are sort of the cross terms, plus x2 times y2, right? So I've taken 1 multiplication of n bits and turned into 4 multiplications of n over 2 bits. Okay, so as we said, we've reduced multiplying n to 4 n over 2s. So if we wrote out the recurrence, it will look something like t of n is equal to 4 times t of n over 2. Okay, I have 4 subproblems, there's half as many bits, plus how much would I need beyond this? Yeah, a constant, except so we're just doing some addition. So once we have the multiplication, and the bit shifting is also relatively, well, it's not so bad. You're just adding up some numbers, right? But it's not actually constant. It's n because here we're actually focused on the bit complexity, so you're adding up n bits. So we're going to keep track of that. So in terms of bits, it's going to be big O then. Okay. So if we write out the recursion tree, right, I have 4 subproblems of size n over 2. Okay, I think even, and here I'll have even more, like that, right? Okay, so what's the total amount of work done at the first level? N, okay. What's the total amount of work done at the second level? 2n. So it'll be 4 times n over 2. And then what would be the work done at the fourth level? It'll be 4n because there's 16 problems, each of which are n over 4. Okay. So now you're starting to see that this is going to look like 2 to the I n. Okay. And how many levels are there? Log n. Okay. So then you're going to be summing up from 1 to log n of n times 2 to the I. So basically 1 plus 2 plus 4 plus 8 all the way up to n. What does that give us? N squared overall. So whenever you get a geometrically increasing sequence, it's dominated by the largest term. So 2 to the log n. Okay. So we haven't really done anything, which maybe makes sense. We haven't really done anything very clever, right? We just kind of, okay. So right now we haven't actually made any progress. Okay. All right. So, go out of order. All right. So I'm going to try to set up Karatsuba's trick and see if you guys can guess it. I don't know if it's very easy to guess, but anyway, once I reveal it, you'll never get to guess again. So, all right, so in the top there, I have what we're trying to, those 4 things, right? And if I'm doing 4 multiplications, that's no good. I don't actually make any running time progress. My goal is to do something clever and try to get it down to 3 multiplications. Okay, so there's still those 4 terms, x1, y1, x1, y2, x2, y1, x2, y2. And I want to try to figure out how to get all those 4 terms with 3 multiplications. Then when we revisit the recursion tree, you'll see we'll make some progress. Okay. And as a hint, I've written a different product. So this is a little different than what we're trying to multiply because I'm not bit shifting x1 and I'm not bit shifting y1, right? So x1 plus x2 just represents an n over 2 plus 1 bit number. Okay, they're like, I took the 2 halves and I've added them on top of each other. Okay, so x1 plus x2 times y1 plus y2 is x1 y1 plus x1 y2, x2 y1 plus x2 y2. Okay, all right. So some of these terms look familiar, right? So for example, this term, of course, matches up with that term. These 2 terms match up with these 2 terms. And this term matches up with that term. That's a second hint. Okay. All right. So any ideas of how to leverage these observations and somehow get those 4, be able to do that top row, but kind of only doing 3 multiplications overall? Yeah. Okay, I think you're thinking the right thing. So how about this? Tell me which are the things, okay, so I'm saying that we only need 3 multiplications, so tell me which 3 things I should multiply. Sorry, you said x1, y1? Oh, okay, so, okay, what's the first multiplication? Oh, you want to do x1 minus y1, wait, x1 minus x2. Okay, what if I told you that it has to be on this screen? Instead of making a new one. I think you're, yeah. Okay, this is probably similar to what you had in mind, but okay, let's look at these. Suppose I multiply those 3 things. Right now I'm just multiplying 3 roughly n over 2 bit numbers. The one on the left might have n over 2 plus 1 bits, but that's not a big deal. Okay, how can I now use that to recover? So I'm missing this middle term, right? Okay, but how would I recover it? now I can just subtract, right? So x1 plus x2, y1 plus y2 minus x1, y1 minus x2, y2 will give us that term, okay? So I multiply x1, y1, which you would have done anyway. I multiply x2 and y2, which you would have done anyway. But to get the middle two terms in one shot, I'm going to multiply that other product, x1 plus x2 times y1 plus y2, and then reuse those original terms to do a subtraction and get what I need, right? We're leveraging the fact that although we don't know how to do multiplication fast, although we're getting close, addition and subtraction was always linear time. So subtracting out the x1, y1 and subtracting out x2, y2 is no big deal. Okay. All right, so in this way, we get it down to 3 multiplications. That's Karatsuba's trick. Okay. All right, now let's make that into an algorithm. As usual, I force us to write a quick sentence before we implement this thing. Anyone want to suggest a sentence? Yeah. Okay. Right, something like this. So yeah, given integers a, b, I guess in binary, return a times b in binary or something, right? Okay, fine. Just so we know what, this is important if we're going to do recursive call for formality's sake, because we need to know that the recursive call will return what we expect. Okay, that's what I had in mind. All right, if we want, oh, that's not correct. Okay, fine. Okay, so we have our sentence, which is just I want to take two numbers and I want to multiply them. Now, if I want to implement this, okay, I mean, it's just good practice to walk through an implementation together, or to coax it out of you guys instead of just showing you the code. All right, how would we implement this? Okay, break it into halves. Okay, uh, sure. All right, so we can like let A0 this kind of thing. So this represents the first half and the second half of the bits, and yeah, just make sure to round up because otherwise sometimes people think you round down by default. But since we're starting with index 1 here, you probably want to round up. Okay, okay, and then B would be something similar. Okay, I'm just being sloppy since we're doing it live. Okay, and then, okay, you would recurse, you write the code down. But I want to just point out one thing. Okay, so you imagine we do the rest. I think we agree on what the rest is going to look like. But even with this, we're missing one thing. Okay, if we did skip over the base cases, so if n is equal to 1, return a1 times b1. Okay. Anything else we're missing? I think it's always good to double check n is equal to 0. Especially because sometimes those recursive calls, if you're not careful about your indices, will occasionally pass down It just put in extra base cases. They're safe, they're easy. You don't have to worry about as many fence post errors. Okay. All right. Okay, so I think that's just roughly what this code is. You multiply it, you add it back together, you bit shift some stuff. Okay, this code, of course, as usual, looks more complicated than it really is. Okay. All right, let's work through the running time. If I wanted to model this recursively, t of n is equal to what? 3tn over 2 plus big O of n. We write the recursion tree, something like this, right? So we have one problem of size n at the top, 3 problems of size n over 2. Next level, you're going to have 9 total problems of size n over 4. Okay. All right. What's the total work at the top level? N. What's the total work at the second level? 3 halves times n. And what would be the third level? Yeah, 9/4 or 3 half squared. Okay. In general, at the ith level, what would it look like? Don't whisper it. Okay. In general, the ith level is going to be like 3 halves to the I. N. Okay. All right. So this is already looking better, right? Because before we had a factor of 2, 3 halves is obviously smaller than 2. Let's see what it really comes out to. Okay. All right, so I have a geometric series, right? So the n could be put on the outside. I really have 3 halves times 3 halves squared times 3 half cubed times 3 half to the fourth, all the way up to 3 halves to the log base 2 of n. Okay. So what does that come out to up to constants? I mean, that sum is a little messy, right? Uh, is this what you're suggesting? N times 3 over 2? Oh, n to the power of 3 over 2. No, not really. So let me do one thing. I can put the n on the outside because, I mean, what we're really grappling it with is this sum, right? I mean, the n could be pulled out. So, all right, how do I evaluate this geometrically increasing sequence? It's messy, isn't it? It's not as easy to see as powers of 2. Sorry? Yeah, so up to constants, okay, maybe up to a factor of 2 or something, for any geometrically increasing sequence. So in this case, it's 3 halves, 3 halves, 3 halves squares, 3 halves. And you're adding them all up. The biggest term is going to be like a constant fraction of the overall sum. Okay, so I even show it in the notes in the back. Okay, but it's always dominated by the largest term when it's a geometrically increasing sequence. Okay, so up to constants, because really it's going to be something like 3 halves to the log 2n minus 1 over 3 halves minus 1 or something like that would be the actual thing if you looked it up on Wikipedia. And basically none of these terms matter. So, okay. So you get big O of n times 3 halves to the log base 2 of n. And here it's actually helpful to keep track of the base. Okay. But the point is, if you see a geometrically increasing sequence, you just recognize, oh, it's the largest term that matters. Right? And the nice thing is that if you have these mathematical shortcuts, then you can really focus on the algorithmic parts, the really interesting parts, instead of this, fighting over constants. What constants, the sort of ignoring constants let you do is really focus on the main ideas, the combinatorial ideas. Okay, okay, this is still a little bit messy. This is accurate, but it's messy. I want to kind of make this nice and clean. So how can I address the 3 halves of log base 2 of n? Okay, sorry, say it again. Yeah. Okay, so you're saying that this part, oh, okay. Okay, that's true. Let me okay, so for those who forgot how to change bases and logs because maybe it's been a while, here's my extremely lazy primitive way to roughly do the same thing. Okay. So, okay, there's this n, and then I take the 3/2 and I write this as 2 to the log base 2 of 3/2 times log base 2 of n. So I just took 3/2 and I just did 2 to the log base 2 of 3/2, right? Because that's how logs and exponentials work, right? And this I'm very comfortable with this rule, okay? And now I can interchange the order of the exponents, okay? So equals big O of n, 2 to the log base 2 of n times log base 2 of 3/2. Okay, so that's fine. You can always change the order in the exponents because it's just multiplying two things together. That also you should be comfortable with. Okay, and now this is nice and clean, right? What does this come out to? N. Okay, good. So now we have n times n to the log base 2 of 3/2. Okay, that might be better expressed as n to the 1 plus log base 2 of 3/2. All right, how do I make this just a little bit cleaner? So that's log base 2, 3/2 is log base 2 of 3 minus log base 2 of 2, and log base 2 of 2 is 1. Okay, so that cancels out with the 1 plus, and we're left with n to the log base 2 of 3. Okay, and n to the log base 2 of 3 is like 1.585. Okay, so it should be a little bit smaller than 1.585. Okay, so that's better than n squared. Right? We've gone from n squared from 2 to 1.585. We reduced the exponent. We have a better polynomial running time based on Karatsuba's trick. Okay. Very, very simple, cute trick. There's lots of historical significance. All right. Any questions? Okay. I wonder if we'll finish early today. I'm not very good about finishing early. All right, so let's do the second part, fast Fourier transforms. This is something that has a lot of real world applications and signal processing, stuff like that. Not that I'm an expert on that, so I can't really explain those details, but I'll give a different application. I think that it has a reputation for being complicated, but I'll try to suggest to you that it's not. Okay, so I think we'll try to take an algorithmic perspective that hopefully will render it relatively simple. Okay. I think the only thing awkward about teaching this is that it does involve the complex numbers, which we don't deal with quite as often. So I've just kind of put together a quick primer of like 2 or 3 slides of just the basic rules we need, no proofs about complex numbers. You guys have probably seen many of these things before, but it'll be enough to study and analyze the fast Fourier transform. Okay. So I think, as probably most of you know, complex numbers are kind of like pairs of coordinates. You have a real coordinate and you have an imaginary coordinate, a plus bi, okay? So I is quote unquote imaginary I. The only thing that matters about it is that I squared is equal to -1, okay? And in fact, if you have something that's equal to where, if you have some value x where x squared is equal to -1, actually lots of nice things work out mathematically. For example, over the complex numbers, every polynomial of degree n has n complex roots. Right? That's not true. You don't have n real roots because in particular, x squared is equal to -1 doesn't have any roots. Okay. So you get a lot of nice things. I don't know if anyone's taken a class on complex analysis, but it's just like all of the best coincidences in math just fall out at once, like Liouville's theorem, all these nice things. Okay. All right, so when you multiply two complex numbers together, which is really kind of multiplying two sets of two numbers. Okay. Thought I had this. Okay. So if I'm multiplying two complex numbers, a plus bi times c plus di, that should be probably similar to what you'd expect algebraically, right? Like the a distributes you get a times c, right? And then you get the cross terms, bci plus adi, right? And then the only kind of funny thing is that bi times di becomes negative b times d because that I squared becomes -1. Yeah, that's the only difference, but yeah, I mean, it's just a simple rule. But once you establish multiplication and we say, okay, that's fine, that's comfortable, there's no surprises there, then of course we also have, polynomials, right? So I can define a polynomial with complex coefficients. P of x is equal to a0 plus a1 times x plus a2 times x squared and stuff like that, right? So, we can start putting math back together just like we're used to. It's just that, and we're still multiplying and stuff like that. Okay, so polynomials also make sense. That also means that if you have any like funky function that can be represented as a polynomial, normally over the reals, you can extend that to a definition over the complex numbers by using this polynomial definition. So in particular, the exponential function, right? In other words, what is the exponential of a complex number? That might seem a little confusing to ask directly, but we know that we can write e to the x as a power series, right? So e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial on to infinity. That's actually always a convergence sequence, kind of like those numbers rapidly approach the partial sums, like the first 5 terms, the first 6 terms, will rapidly approach the solution because that factorial grows so fast that the far end terms don't contribute that much. So that's a really rapidly converging power series. So in other words, I can talk about e to the x where x is a complex number, and it makes sense because we have a power series representation. We can fall back on that. Okay. All right, so complex numbers, not too many surprises compared to regular numbers. All right. Here's some kind of where some nice coincidences start to come into play. Euler shows up for the second time in this class. Okay, so we can look at the value of e to the theta I, where theta is some value between 0 and 2 pi. So you can think of it as an angle. Okay, and Euler's formula states that e to the theta I, okay, the real part, the real coordinate is going to be given by cosine times theta. And sort of the imaginary coordinate, the b, if it's a plus bi, is given by sine theta. Okay, so with complex numbers, actually, there's very nice geometric interpretation. Okay, all right, so you don't get that with regular numbers. And as a result, you get these sort of famous identities. So e to the pi I, so that's 180 degrees, right? And that would take you here. So that's just -1. Okay. E to the 2 pi I would be a full circle and get you back to 1. Okay, so you get these nice identities. E to the 2 pi I is equal to 1. E to the pi I is equal to -1. Okay. This is going to be very useful in a moment. Okay. All right. So this fast Fourier transform is going to be focused on the so-called nth roots of unity. Okay, so what is nth root of unity? So it's any complex number, omega, such that omega to the n is equal to it's equal to 1. Okay? So any number where you raise it to the nth power, that's equal to 1. So what's an example of an nth root of unity? for any n? What's the simplest one? Sorry? I? Uh, well, if n is 1, then actually I to the 1 is just I, so it's not equal to 1. Uh, 0 to the n is also equal to 0, so that's no good. Omega. Oh, well, yeah, what is an example of a valid choice of omega that always works? Just to make sure we're on the same page. What's the easiest one? 1. Okay, so that's one root of unity, right? 1 to the n is always equal to 1. If n is even, then what would also be another root of unity? Huh? I? Well, what about 2? I squared is negative 1. So negative 1 would always work if n is even. Okay, now what if n is like a power of 4? Then I is okay, because I squared will give you negative 1. Square that again will give you. Okay, so those are some really simple examples. Okay. What about for general n? Or what's kind of a systematic way to generate a lot of roots of unity for something weird like 7? So 1 would count, but there might be others. What would be a 7th root of unity? Yeah, so Euler's identity. Okay, so Euler's identity, very nice. Okay, so if so let's let omega sub n be 2 to the pi I over n. Okay, and it's sort of spinning around this circle here. And so if I raise this, okay, so if I raise this to the nth power, right, then I just get e to the 2 pi I. The divided by n cancels out. And then, as we know, that just brings me back to the beginning of the circle. Okay, so raising it to the nth power, so there's actually 16 dots hopefully around. You know, each power is just gradually ticking and going around the clock. So by the time you go 16, you get back to that first spot on the right. Okay. All right. So in fact, any other roots of unity besides that one? So right now we have 1 and sort of omega sub n for any particular n. 2. So if this was, if I looked at omega sub n squared, right, which like for 16 would be this value. Okay. If I raise this to the nth power, then I'll get omega sub n to the n squared, and I'll get 1 squared, and that's 1. Okay, so that's another one. Okay, any other ideas besides 2? Okay, we can go all the way around this clock. Each of these values, the third power, the fourth power, the fifth power. Okay, each of this represents a distinct root of unity. Okay, so you need Euler's formula to see this, and in fact, that gives all n roots of unity. Okay, because we know that, you know, this polynomial x to the n is equal to 1 only has n zeros. So as soon as I find those n roots of unity, I know I found all of them. Okay, because you can factor it. Okay. All right. Okay, so those are the n roots of unity, which is really kind of just chopping up this circle like a clock. All right. Somehow this is going to be very useful. Okay, so with all that complex analysis facts behind us, let me now explain what the discrete Fourier transform does. Okay, so at some level, the input and output is very simple. It takes as input n values, and it outputs n values. Okay, so we'll never stray from that. Okay, what are these n values? So you're given these values a, and you will see y indexed by 0, a0, a1, a2, up through an minus 1. That's n values. Okay, And what we're going to do is we're going to think about that as the coefficients of a polynomial. So the output is going to be, so f sub n of a, so f sub n is what I'll call the Fourier transform for size n, like with n inputs. So put that polynomial together, a0 plus a1x plus a1x plus a2x squared. No. Plus a2x squared plus a3x cubed and so forth, right? So I'm interpreting the a's as the coefficients of a polynomial, and I'm evaluating the polynomial at each of the n roots of unity. That gives me n different values. So I evaluate p of 1, p of 2, p of 3, sorry, p of 1, p of omega sub n, p of omega sub n squared, p of omega sub n cubed, all the way on to p of omega sub n to the n minus 1. So I evaluate p at each of the n roots of unity. And I output those values. Okay, that is the input and the output of the discrete Fourier transform. Okay, nothing special. How long would that take in a straightforward fashion? Like, what's the most natural way to do this? So assume you can multiply numbers and add numbers in constant time. Don't worry about the bit complexity from the first part of the lecture. Now we're just kind of assuming we can multiply and add like we usually do. Sorry? One more time. Just plug in, just evaluate each of them, right? So how long would it take to compute P of 1? How long would it take to compute P of 1? N time, right? We just a0 plus a1 plus a2. And then same was the first one, right? That would also take some omega sub n, n time. So each of these would take n time to evaluate, okay? It's just going to be like n multiplications and additions, bringing it all together. And there's n of them, so you would take n squared time to do this naively. Okay, so the question is, can we do better? Okay, so it's important to mention that besides the Fourier transform, there's sort of an inverse thing. It's actually awfully similar. It's called the conjugate Fourier transform. It's almost the same. Okay, there's a good reason for it, mathematical reason. But the input again is n values. And again, the output is n values, which are again evaluating at the roots of unity. But the only difference is they're listed backwards. So in one hand, we were going, I guess, originally counterclockwise around that circle. Is that from your point of view correct? I'm not sure. Okay, we're going counterclockwise with the 1 omega sub n squared, omega sub n cubed. And then this time, we're just going the opposite direction, 1 omega sub n to the n minus 1, omega sub n to the n minus 2. Okay, and just going the opposite direction. Particularly an algorithm for one is an algorithm for the other, because if I can do f sub n, then to do f sub n star, I would just do f sub n and then list the values in opposite direction. So algorithmically, there's no difference, okay? But it still has some mathematical significance. Let me explain, okay? So they're essentially inverse to one another. In fact, they can like undo each other, so to speak. So if I evaluate f sub n of a, okay, so that means that I take a, which is n values, I interpret that as the coefficients of a polynomial, I evaluate that polynomial all over the roots of unity. So now I have n values, okay, and now I interpret those values as coefficients of a polynomial, and I evaluate all the roots of unity except in the other direction, f star of n, then I'm actually going to get back a, except it's multiplied up by n. So everything's scaled up by a factor of n, but then you can just divide by n to recover a. Right? So dividing by n at the end is not a big deal. So f star of n actually undoes f sub n, and also vice versa. If you compute f star of n first and then you do f sub n, you'll recover a up to a factor of n. Okay, so not only can we, so really what's going on is not only do we want to compute the Fourier transform fast, but we want to be able to compute its inverse, essentially inverse, because dividing by n is easy, very fast as well. Okay. All right, so that is going to be, what we'll spend most of our time focusing on, trying to get an n log n, like sorting basically, running time for this problem, right? It's pretty impressive because it feels like you should be multiplying n squared things and adding up n squared things, but we're going to somehow take advantage of these roots of unity and some structure to only have to do n log n kind of additions and multiplications and stuff like that. All right. Now, before doing the algorithm though, I wanted to give some motivation, and there's lots of real motivation like related to electrical engineering that you can read the Wikipedia about. I'm not the best person to explain that stuff, so let me give you something that doesn't require any kind of definitions or any real world details. Okay, so let's look at the basic situation of you have two polynomials and you want to multiply them together. I died. All right, sorry guys, this is a bad luck day. All right, how does that sound? Okay, sorry about that. All right, let's get jazzed up again. All right, so this basic situation is you want to multiply two polynomials together. That's simple enough, right? We know what polynomials are. It'd be interesting to multiply them together. So I give you a polynomial p of x with coefficients given by the a's. I give you a polynomial q of x, coefficients given by the b's. And I want to compute their product r of x, which is equal to p of x times q of x. I want to compute their coefficients. Okay, so now it's some c0 plus c1 all the way up to, I guess the biggest degree would now be x to the 2n minus 2. So the polynomial gets bigger when you multiply them together. Okay, so now in general, the coefficients, we can write them as like, if I'm looking at degree 10, right, the coefficient for degree 10, then that's going to be the sum of like a0 times b10 plus a1 times b9 plus a2 times b8, right? Because that's how we get all the x to the 10s from x squared times x to the 8, x cubed times x to the 7 and stuff like that, right? So that's called a convolution. So if I wanted to, multiply these polynomials the old-fashioned way and just compute those coefficients directly, how long would that take? Roughly n squared, because you end up multiplying all the pairs of coefficients together. Every AI is going to get multiplied times every bj. Okay, so that would take n squared time. And now the goal is to do faster. Okay, all right, so again, I'm going to give you guys a chance to guess. Anyone want to try to guess how to multiply polynomials faster using the fast Fourier transform? And you don't have to guess the full solution, just to suggest some ideas. Any ideas? Sorry? Reverse one of them and split them in half. So actually what I'm thinking is going to be trying to use the fast Fourier transform as a black box. So the fast Fourier transform is going to do some splitting in half. It's going to do some divide and conquer in it. But at this level, I'm just trying to kind of model and show why FFT is useful. All right, so let me give a hint. Okay, so here is an idea. Okay, so there's the polynomials, there's our goal. Okay, so here's an idea. Let's see if it sparks any. Oh, where's the idea? Okay, here's the idea. All right, I know that for any 2n root of unity, I use 2n because r now has roughly degree 2n. Okay, I know that r evaluated as some 2nth root of unity is equal to p times that root at that root of unity times q at that root of unity, right? Because that's also what it means to multiply polynomials together. Does this inspire any ideas? I can get rid of the highest power. Well, so I could have written 2n minus 2 instead of 2n, but I just, 2n's fine and it's notationally simpler.
We can get rid of the highest power because omega sum of all the powers should add to 0.
Oh, Um, so that's true, and that actually shows up in the proof of the inverse part. But no, that's not the direction I'm trying to go here. Yeah, I want to use yeah.
Yeah, first do the Fourier transform
Uh-huh.
and then multiply the e and multiply each constant of the same order.
So let's multiply something together. So okay, take some Fourier transform, multiply some things together.
Multiply the coefficients of the same order. Same order.
Oh, okay, coefficients of same order.
And then inverse circle. Inverse circle.
Okay, we'll try to invert. Okay, so let me think this. Okay, so you start with two polynomials, right? P and Q. And so the idea was step one, let's take their Fourier transform. That'll give us all of those values, right, at the roots of unity. Okay, so I spend n log n time. We haven't proven that, but we will. And I get all of the values of the roots of unity. So all of those p of omega sub 2n to the I. Right? I get that for all values of I in n log n time. Okay. And now, so I have all the p and q values. Right? And now to get to r values, I just walk through and multiply them together, like zip them up. Okay, so multiply the product of for the first root unity, the second root unity, third. Okay, so I multiply them pairwise, and that just takes linear time. And then at that point, I have all the values of r at the roots of unity. That's the Fourier transform of the corresponding coefficients, right? So now I have the Fourier transform of the polynomial I want, or the coefficients of the polynomial I want. And finally, to get the polynomial, I do what? Yeah, we just call the inverse, and we divide by 2n and stuff to get, okay? So I call the inverse operation, and then I get those coefficients c up to a factor of 2 times n, which I can divide out, okay? So somehow we're able to multiply two polynomials together. You would think you'd have to multiply all pairs of coefficients, but we do this Fourier transform trick, and we only need n log n time, right? I always find this quote pretty compelling. Okay. So F2NA is the Fourier transform of A for 2n coefficients. We haven't done the algorithm yet. I'm just trying to show why it's useful before we now go into the algorithm. So I'm assuming I can compute in n log n time for this part. All right, how fun. Okay, so with that in hand, we have 15 minutes left. I think that's plenty of time because the algorithm's actually not that complicated to try to compute f sub n of a in n log n time. I'm just going to focus on f sub n of a because obviously f star n of a follows from just rearranging the output. All right. Okay, so where do we start? Okay. So somehow, these things come down to these simple ideas. The most important thing that we're going to leverage, okay, I'm going to assume we're going to leverage the simple fact that the 2nth root of unity, right, if I square it, I get the nth root of unity. Okay, that just comes from, if I went back to like the clock, right? So this was like 16 roots of unity, and the 8 roots of unity is every other one, right? This would be the eighth roots of unity. Okay, if I take omega sub 16, the 16th root of unity, I squared it, I would get the first 8th root of unity. Okay, no big deal. All right, so somehow we're going to leverage this. This is what the trick is going to be. Okay, simple. All right, so what do we want to compute? Uh, let's look at, I want to compute 2n different values. Let's look at the kth one for some generic k. Okay, so that's And I just plugged in omega sub 2 to the 2nth root of unity to the k into the polynomial, right? So I have a1 times nth root of unity to the k all the way down to 2n minus 1. Okay. All right. So somehow we're going to try to split this up. And I want to give you guys a chance to guess. Don't know if it's easy to guess for those who haven't seen it before. Any ideas of how to do divide and conquer on this? Odd powers, even powers. Have you seen this before? Okay, well, that's a good guess. Okay, good. All right. Okay, so let's look at here. What I've done is I've just split it up into two sums where one represents sort of the even index coefficients and the other represents the odd index coefficients. Okay, so if you look up top, you see A0, A2, and there would be an A4 onto A to the 2n minus 2. And then below I have A1, A3, A5, A to the 2n minus 1. So I just took one pile split into two. But instead of splitting in half like down a median or something, we did odd and even, which is a little different than we've done before. Okay. All right. So let's look at the even coefficients first. Okay. So how can I simplify this expression a little bit? Yeah. Yeah, so at some level I can take this squared, okay, and use that to cancel out the 2 and the 2n. So first we swap, k times 2 becomes 2 times k. I put 2 on the inside, and I have omega squared sub 2n, and that's omega sub n. Okay. Same here. This would kind of become 2. This would become n minus 1, and I can get rid of this 2 down there. Okay. So I can cancel out. I can do this squaring idea. Okay. And now I'm looking at a bunch of nth roots of unity. Okay. And so what is this? This can be thought of as the Fourier transform, nth discrete Fourier transform of the polynomial, of just the even coefficients. Okay. And it's the kth term of that. Right? So that sum representing the even part originally has now sort of been turned into something that looks like a recursive subcall with n over 2 with a smaller number of pieces. Or I guess n, because I'm doing 2n, from 2n to n. Okay. Odd, we can do something similar. This seems like this should be a 3. Okay. So for odd, we can do something similar. The only kind of difference about the odd case, okay, so what's the issue here? Sorry? There's an extra omega sub 2n. There's an extra 2nth power of unity. So, before we had those even exponents, so they can just cancel out. I can divide by 2 up top and cancel out a 2 on the bottom. Now it's odd because I have an extra one in there. So all I have to do is pull out one factor outside the parentheses and subtract 1 from all the exponents. And then I can do this canceling out the even number trick. Okay. So, oh man. Okay, so if I pull one out, and then I do this doubling trick, where the 2nth root of unity squared gives me an nth root of unity, okay? Now I get something very similar for odd, except it's multiplied by one extra factor, okay? And again, this looks like a recursive subcall, where I take the Fourier transform now with n coefficients on the odd coefficients, the odd indices. And I take the output and I also multiply it by one factor of omega sub 2n. Okay. All right, so good. So now we're starting to see some things come together. When I go back to the original thing, I plug it back in. Now I start to have something that looks a little bit more recursive. Okay. I don't know what's going on. Okay. All right. So, okay. Now, who wants to deliver the final blow and guess the algorithm? I forgot to write the sentence, so I'll say it out loud. You're given one coefficient. You're given a vector of n values, and you want to output the n values corresponding to the Fourier transform of those n values. Okay. Who wants to try to guess the algorithm before I unveil it? Given some of the math we've done to justify an algorithm. What would the algorithm look like? So I'll just get you started. FFT, your input, something like that. Divided to even. So wait, let's do the easy stuff first. What's the easiest stuff? Recursive algorithm. What's the easiest thing? Okay, just quickly do some base cases. Otherwise, I have to leave an awkward gap there. All right, so if n is equal to 0, then I should return, I guess, like an empty list of values, right? There's no, I'll write this for empty list. I don't know. We're not, we still have time, right? Okay. All right, I've been off before. All right, n is equal to 1, and we would return. Return A0. I guess the list of that only consists of A0. We should be returning a list of values. Okay. Otherwise, I think it was suggested we split into odd and even. So somehow we like, okay, now I'll just show the code. All right. N equals 0, return empty list. N equals 1, return the first coefficient. All right, otherwise, I guess I'm letting the y's represent the values of a subcall to A even, where A even is the even coefficients that takes linear time to put together. The z's represent the output, if I call it to A odd. Okay. And then I return the combined values, I guess x0 through xn minus 1, where xk is equal to yk plus omega sub n to the k z k. Okay, and then that's it. The correctness was justified in the previous slide. Okay, so ultimately this Fourier transform is very simple. It's just divide and conquer into the even coefficients and the odd coefficients, and that's it, you're done. The only reason we get away with this trick is because these roots of unity are so well behaved when they're powers of 2. It's really just coming down to this root of unity 2n squared is the root of unity, the nth root of unity. That's it. Nothing special. Okay. All right. What's the running time? I've got to start it. T of n is equal to. Okay, I think I heard this. 2 Tn over 2, because you're splitting the input into half. I mean, splitting the number of values in half and then doing subcalls, plus O of n. So this is coming from either assembling A even, assembling A odd, or adding things back together at the end. Okay, and what's that? Yeah, this is the one we see all the time. Same as merge sort, n log n. Okay. All right, so we actually finished early today. That's all I had for us. Maybe one topic I omitted was matrix multiplication, which if you're curious about, you can look at the notes. But at some level, if you have two matrices, say n by n, and you're multiplying them together, the standard thing will give you n cubed. Okay, but sort of in a Karatsuba style way, like we did for integer multiplication. There's sort of a nice way to chop it up. Like you take your two n by n matrices and you look at kind of the four corners of each, and you can reassemble it in a weird way. And instead of naturally doing 8 multiplications, you can do 7. Right? I mean, out of those corners, you would naturally get 8 multiplications. You could turn it into 7. Um, it's a bit complicated. It's hard for me to explain the intuition, but you can verify it works. And in that way, you can actually do faster than n cubed. Okay, and then it's actually been increasingly improved over time. And so the conjecture is that you can do n squared matrix multiplication. And right now, the best bound is like n to the 2.323 or something, 232 or something. And like I think like the fifth decimal digit was recently improved. Like there's very tiny improvements to matrix multiplication, and the algorithm's so complicated that the hidden constant actually makes it not worth it to implement it at this point. But it's still an interesting theoretical question to get it down to n squared. So it's nice to be aware of this. Okay, then that's all I had, and I'll see you guys Wednesday.